Thank you very much. Okay, so a highly consistent finding across a wide range of functional imaging studies is that increases in frontoparietal control and attention regions during externally directed cognitive control tasks, and that of relative activation decreases in regions of the default mode network. These task-induced deactivations have been attributed to a role for the default mode network, DMN, in internally directed or self-referential cognition. However, it's important to note that an inherent assumption of this interpretation, or of a meaningful interpretation of default mode network deactivations in general, is that task-induced deactivations follow the same neurovascular principles as task-induced activations. Or in other words, that relative decreases in Bolt signal during task indicate a relative decrease in neural activity. And of course, this assumption is very difficult to test in humans directly. So in the current study, we use a novel imaging approach to assess transient changes in glucose consumption directly in conjunction with task-induced fMRI deactivations in the default mode network. And here we consider glucose metabolism as a surrogate marker of neural activity that is independent of vascular coupling. The working hypothesis that we started this work with is that glucose metabolism will parallel changes in Bolt signal, so that there's an increase in glucose consumption during a task active comparison, so task greater than rest, and a relative decrease in glucose consumption on the flip side of the contrast. We use a novel imaging approach called functional FDG PET that was pioneered by Villiers et al. At the Martinos Center to measure task-induced transient change in glucose consumption. So here is the image from their paper, where they showed that when you infuse FDG, instead of giving a bolus at the beginning, you slowly infuse FDG constantly throughout the scan. And that way you can tease apart transient and subtle changes in glucose consumption as an increase in slope during a task. So here it's shown for the visual cortex with the red line during a checkerboard. And then as a control region, here is a region not involved in the task in the frontal cortex. And you can identify those changes voxel-wise with a general linear model. In our study, we used a slightly different design. So we had 3 different task conditions during a 60-minute scan. The first one, each condition lasted 6 minutes. So the first condition, hereby indicated by the cross, is a resting state scan with eyes open, where the participant is just asked to rest. And then we have 2 working memory conditions. So one is a difficult working memory manipulation acquired during 6 minutes with indicated here with the dark blue bars. And during that condition, the participant is presented with 2 letters first, and then a short maintenance period, and then a target letter, a probe letter with a question whether this letter followed either of the target letters in the alphabet. So the participant is required to maintain, but also manipulate stimuli in working memory. For the easy working memory maintenance condition, the participant was required to just maintain letters and not do the manipulation. We acquire this data on a GE-Signa PET-MR scanner so that we can acquire both functional PET FDG throughout the scan, but also a continuous run of fMRI of 42 minutes that started at around 18 minutes, as indicated there. And I will show data from 23 young subjects, and the data here is just fitted with a general linear model for both modalities separately to model both task conditions and the rest. And those results I will show now. So the first pattern of results shows that task-induced activations converge very well. So on the left, you see the typical fMRI pattern for the contrast manipulation versus rest, so the more difficult working memory condition versus resting state. And you see fMRI activity in widespread lateral, prefrontal, and parietal areas, overlapping with regions of the frontoparietal control network and the dorsal attention areas. Nothing new there. And we see that the functional PET data actually mirrors these activations very well. So these data now show increases where there's activity or where there's red-yellow This shows increases in glucose consumption during the working memory condition versus rest. And here's an overlap map where a brighter color indicates that both modalities have higher statistical significance, showing that there's a good overlap between both modalities in the frontoparietal control areas on both hemispheres, particularly so on the left because it's a verbal working memory task. We also see that both modalities scale well with task demand. So if we go to the contrast not versus rest, but manipulation versus maintenance, so difficult versus easy working memory, we see an increase in activity for both fMRI and PET in task-relevant regions. So now if we go back to the manipulation versus rest contrast here, and just focus in on that, to appreciate also the deactivations, so the flip side of the contrast. And we see, of course, on the medial surface here, the default mode network deactivations. And now I will, instead of overlaying the fMRI activations, I will show the PET data in conjunction with the default mode network deactivations. And what is striking, of course, is that we don't detect any spatial overlap between a change in PET signal and fMRI deactivations. The PET data is here shown for both sides, so there's neither increases nor decreases in glucose consumption in those exact areas where we see fMRI deactivations acquired at the same time. So task-induced deactivations do not converge. It is important to note that for correctly interpreting this lack of overlap, to note that our FDG data, despite the unusual infusion protocol, looks pretty normal before the task started. So the posterior cingulate here that is deactivated in fMRI is still one of the most metabolically active areas during rest. So a more accurate interpretation than saying that there's no glucose change is that glucose metabolism remains high in the activated regions, even when individuals transition between rest and a working memory task. Moreover, a closer look at the PET active regions here reveals two different patterns. So for one, we have those regions which are shown here as an example, labeled A, which also can be found on the lateral surface, where there's the overlap that I was presenting at the beginning. So both FDG and fMRI overlap very well. But then we also detect a set of regions where we have increases in FDG signal during the task. So for example, those illustrated here, those labeled B and C here in the posterior midline, where we see really no signal change in fMRI at all. So this is just to highlight that it's also not just a thresholding issue. And if we zoom on this task-induced into these areas that are high metabolically active during task as compared to rest, but have no corresponding fMRI signal, we see that they actually fall along the borders between the default mode network and the frontoparietal control network. If I zoom in and indicate the borders here based on the Europacylation. Both in the posterior midline and in the inferior parietal cortex, we detect this kind of pattern. And interestingly, we also see a similar pattern in the stratum, shown here in the volume, overlaid on the Troy pacylation, corresponding to EOS 7 networks, where we see high metabolic activity during the task in the dorsal caudate, but no corresponding fMRI signal. So in summary, we detect three interesting patterns of result here. First of all, as kind of a proof of concept, we saw that hybrid FDG, FPET, fMRI reveals good spatial overlap in transient increases of fMRI and FDG in task-relevant areas. But we find no evidence for transient changes in glucose metabolism overlapping with the default mode network deactivations. Instead, we have identified a set of task-induced FDG activations that emerge adjacent to task-induced deactivations, but with no direct spatial overlap, also including the stratum. So what does that mean for our understanding of cognition and the function of the default mode network? Well, I think the data suggests that fMRI deactivations cannot just be simply labeled just another task, and the data are also challenging to reconcile with the notion of deactivations as suspended activity, because we don't, in those exact areas, see a relative increase in glucose consumption during rest. So our hypothesis was in that way not confirmed, and the pattern would look more like indicated in this. I'm also not really ready to say that that means that fMRI deactivations are completely vascular, like for example vascular steel interpretation, because we have identified these sets of metabolically active regions just bordering the deactivations, and I think they will require some further thought and analysis to see if those can be functionally linked to the deactivations. So instead, I think those data are challenging us to consider whether neurovascular or how neurovascular coupling may not be uniform, not only across large-scale association networks, but also maybe between different cognitive states. I want to acknowledge everyone in my lab. Lars Jonasson is the postdoc who did the work, and he was supposed to present the data, but he couldn't be here today. And everyone else that was involved in this work. And particularly Katrin Rieckmann and Lars Nyberg, who are the directors of the Umeå Center for Functional Brain Imaging, and the Department of Nuclear Medicine, who have been very supportive in us getting access to the scanner. A collaborator, Andreas Hahn from the Medical University of Vienna, my ERC starting grant for financing the study. And then I also want to quickly take the last few seconds to say that I, together with a bunch of other people who have used PET-MR, have started a simultaneous PET-MR scientific interest group via the International Society of Cerebral Blood Flow and Metabolism. We have our kickoff event in Japan in a month from now at the brain meeting. So if you're interested, you can sign up at the link given there. Thank you very much.
Thank you.